This morning, I wanted to talk about accelerating your software development lifecycle, specifically accelerating development and testing using data virtualization. Just in case you're worried, I'm not a salesperson. I've been an Oracle database administrator for about 20 years and a programmer analyst for about 34 years, a bit too long, but I have been working at Delphix for about 3 years. I've got a couple of books under my belt on Oracle data warehousing, a couple of books on database administration, one book on the beginning Oracle SQL language. Over the years, I've picked up a few affiliations. I'm an Oracle ACE director. I work with the Oak Table Network, and I'm a board member of the Rocky Mountain Oracle User Group here in the U.S., and I'm also a past board member of the ODTUG Oracle Developer Tools User Group. I live in Colorado and married to Kellen, who's also known as DBA Kevlar, and between us we've got 5 kids, almost all fully grown, so it's a wonderful thing. But enough about me. Over those 34 years in IT, I've been a developer where my job is to create new functionality, fix bugs, things like that. Great new job. Great part of my job. I've also been a tester, of course. That's where you take your programmer hat off and you make sure that all the software, someone else's software, works as designed, because it's very difficult to test your own software. But I have been a tester, and for the majority of my career, I was a database administrator, where my job was to create databases, protect them, job number 1, and keep the applications running optimally. So all of these things are in this presentation, all of these job roles, but mostly I want to talk about change. Okay, and the question is, where things are pretty busy these days, and the question becomes, are you too busy to change? I hope not. So when we talk about change, for the most part, we're talking about virtualization. In broad terms, virtualization is the conversion of the data center from hardware that has to be installed into automatable software. Server virtualization is the norm for systems administration today. Server virtualization only virtualizes CPU, RAM, and network, that is, compute. Server virtualization includes packages like VMware, KVM, etc. But interestingly enough, it really doesn't do much to virtualize storage and databases. As an end result, data virtualization is the rest of the entire virtualization solution. And if you haven't been absolutely amazed by the benefits of server virtualization over the past decade, then that is because data virtualization, the other half of the solution, has been missing. So you only have the partial solution, and even so, it's been great to have, but we can now make it even better. Stop for a moment, consider, what are the distortions that have arisen in the software development lifecycle prior to the advent of server virtualization and data virtualization? Specifically, ask yourself how many non-production environments your organization supports for doing software development lifecycle. Stop and think, behind every production application, how many non-production applications do you have? Is that enough to carry on software development lifecycle? It's just in bare survival mode? If you think about it, if I ask that question, most people have maybe 3 or 4 non-production environments behind each production environment. They're able to put new software changes, functionality, or fixes into production maybe every couple months, because they've only got those 3 or 4 environments to work with. So no matter how many people you have in your IT shop, whether you're just a one-person shop, whether you're a small shop of maybe a half a dozen people, or maybe you've got several hundred developers and such, if you've only got that small number of environments in which to develop and in which to test, then everything is going to queue at that resource, and it's going to take a lot of time. Now, that's not going to work today. New functionality and fixes, as you know, they have to be delivered to production within hours or days, at most weeks, but not any longer, months and years. The days of a project that take 18 months or 24 months, they have to disappear. There's really not enough time. There's not enough will in the world to take that much time to make changes. So ask yourself, inside your own IT shop, can you maintain such a tempo? Is such a tempo possible, supporting production with, say, a single instance of dev, an instance of SIT, systems integration testing, and user acceptance testing? Here's the litmus test. Can your IT infrastructure support 2-week sprints? Suppose your development teams have moved to agile or lean methodologies, and they want to do 1 week or 2-week sprints. Can your IT infrastructure support that? With brand new environments, newly refreshed from production, ready to go, ready for development, ready for testing. Chances are your answer is 2 weeks. Are you kidding me? I mean, that was the answer I've seen at all my customers, just prior to joining Delphix. So what's going to save us here? Over the past 40 years, Moore's Law has predicted a doubling of processing power every year, or 18 months or 2 years, somewhere like that. And for the most part, interestingly enough, Moore's Law has proven true. But the thing is that software is moving ahead faster than hardware. Even if hardware is doubling every year, 18 months, or 24 months, software has to move faster. We can't implement, we can't deploy, we can't test the requirements that are being made on a daily basis on that kind of rate of growth. So to achieve continuous delivery, continuous integration, we need our infrastructures, our entire IT infrastructure, to become much more efficient, not just more powerful, but more efficient. That's the other side of performance tuning. You can either throw lots of hardware at a problem, or you can do things more efficiently. So let's talk about that. Let's talk about some lessons in efficiency. I don't know if you've had a chance to read this particular book. It's a classic, written back in the 1980s. It's about the manufacturing side of the economy. It's about a factory, essentially. And the great thing about this book is that it's written as a novel. It's a fun read. It's got character development. It's got comedy. It's got tragedy. It's got romance. It's got everything that you might expect in a novel. It's actually a really good book. I mean, the fact that it's also a college level textbook is another thing entirely. And it's a revolutionary college level textbook. So it teaches what's called the theory of constraints. And that the theory of constraints, among other things, teaches us that in manufacturing, having long build cycles is incredibly wasteful. So we have to shorten the build cycles for the things that we manufacture. The other thing that it teaches us is that the testing of the things that we manufacture, are the first victim of our long build cycle. Because as we get to the end of the build cycle, where testing occurs, what's the easiest thing to cut? The easiest thing to cut is, of course, testing. So we're constantly putting manufactured goods that aren't tested, and for that matter, if you think about it, in IT, software that's not tested out there. But here's the most important thing. And this is the reason I read the book in the first place. It was recommended to me by a gentleman named Kerry Millsap. And Kerry is a performance tuning. I just say he knows a lot about performance tuning because he hates the word expert. And the lesson here is that improvement not made at the constraint is a waste of effort, an illusion. So the theory of constraints teaches us to identify constraints and to improve complex processes at the constraint. So think about a factory floor. This is a really simple representation of a factory floor. Let's say we're manufacturing PVC piping. Okay, so we start from the right-hand side, and we move from station to station, just in a single line, all the way from pouring resin into a mold. We trim after it comes out of the mold. We check. We do a little bit of QA for leak detection. Then we label the finished product, cap and fill it. We put it on a pallet for shipping, and then, of course, we ship it out to our customer. Okay, this isn't really a complex system whatsoever, but it's slightly complex in that there are 6 or 7, 7? Yeah, 7 stations involved here. Now, before the goal was written, if this system didn't perform as expected, then we really didn't know how to handle it. Now let's just imagine that the constraint here happens to be the one station that does QA, leak detection. Okay. Now, in the context of the book, in the context of the novel, The Goal, they don't know that it's a constraint, but it is. And they're looking at symptoms such as in the stations ahead of the constraint, they're seeing inventory stockpiling, piling up. So of course, management practice of the day was, well, inventory's piling up, that means the employees aren't working, so punish them. The other symptom that might be seen is downstream from the constraint afterwards, we're seeing starvation. Okay, so management philosophy of the day was, these employees aren't doing anything because there's no inventory, but even so, punish them. When in fact what should happen is that we should take the constraint and we should optimize it. Now in the book, the way they talked about it was the new leak detection machine that was in the factory was the newest, the most up-to-date, state-of-the-art kind of machine whatsoever. It was expensive, it was brand new. It should have been, the best station in the factory. But in fact, it was the reason that the factory was falling behind and going out of business. So what the hero in the novel suggests is, hey, let's take the old machine, the one that we just replaced with this brand new state-of-the-art machine, and put it back in service. And everyone's saying, no, you can't do that. It's too expensive. It costs too much per unit, blah, 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 blah. All kinds of objections. But the fact is that if you can optimize that constraint, then you optimize the entire system. And that's what they did. And I don't want to give any spoilers, but that's only the first of many hurdles that they overcame throughout the novel. So wonderful. Theory of Constraints, great book, really highly recommended. And if you are interested in reading the book, let me know, and I'll try and get you a Kindle copy, an Amazon Kindle copy. Just send me a communication, email or something like that, and I'll try and get you the book. But better than The Goal, which was written back in the early 1980s, somebody, basically Gene Kim and his team of authors, took the lessons behind The Goal and updated it for today's industry of IT, of information technology. So the theory of constraints has been updated with this book, The Phoenix Project. And oh, by the way, no, I'm not I'm not selling these books. I'm just saying they're fantastic. I don't get anything, for sale of these books, but again, I'll be glad to get you a Kindle copy if you're interested, because it's really worthwhile knowing about. So the Phoenix Project is the goal, the book, The Goal for today. Like The Goal, it's a novel. It's an easy read. It's got some funny sections in it. And I think you'll all recognize this. The constraint in the Phoenix Project, which is, of course, about a project called Phoenix. It's supposed to save a particular software company. The constraint is not a machine. It's a guy named Brent. Brent is brilliant. Brent knows everything. In fact, every project has to have a piece of Brent. In other words, nothing moves forward if Brent isn't feeling in top form. Does that sound familiar? Is there someone that has to have their hand in every single project within a company? That might be familiar. That's just one. Again, I'm not giving away spoilers. That's just one of the things that had to be overcome in the Phoenix Project. But again, a fun read and a very educational read as well. So the theory of constraints, which is the goal applied to information technology, also along the way teaches us what is the constraint in information technology. The answer is pretty easy. QA environments and development environments. These are the two things that hold us back from being able to push software out into the world fast enough and of high enough quality. So according to Gene Kim, we have to be able to set up our environments. These are our top constraints in IT. These are the things that slow us down. And if you stop and think about it, you realize it's true. What are the things that slow us down? It's not our developers' ability to code. It's not our testers' ability to run through test scenarios. It's having data that is the problem. They don't have the environments they need to code in. They don't have the environments they need to test in. So data is the constraint, and it's getting much worse. Now, this is kind of funny. At the very bottom of the slide, it says that Gartner predicted a data doomsday by 2017, with 1/3 of IT in crisis due to the lack of data. And you're probably laughing right now. We're into the second third, almost the third of 2017 by now. And you might say to yourself, well, I'm not seeing a data doomsday. But aren't you? You know, this study by Gartner was done in 2014. And between then and now, what has happened that has kind of attenuated the crisis? I would say that it's cloud. Because with cloud, we have almost infinite scalability of our infrastructure. It costs. Oh boy, does it ever cost. But I think that we have the crisis here of infrastructure and being able to provision infrastructure for our developers and testers. But the problem is being drawn out or attenuated by cloud. I mean, eventually, even the cloud won't be have enough resources to deal with the problem. So here's our constraint as developers, as testers. Data is the constraint. What can we do to resolve it? Well, again, looking at the problem, production, is the environment that we care most about because it's the environment that runs our businesses. But behind every prod, there's a QA test environment or a SIT environment or a UAT environment, okay, a dev environment, other project-specific environments, a training environment, a scratch environment for patching, et cetera, and so forth. Now, here's something. If you're going to be cloning prod to make these other downstream environments, well, remember, prod is growing. I mean, that is, if you're lucky, prod is growing. And hopefully we're all doing our jobs well enough so that we're lucky. So as prod grows, that means that these downstream environments are bound to grow as well, unless we can do something to shrink them, right? So anyway, everything is growing bigger and bigger and bigger. Inevitably, the situation shifts from an org chart that looks like this with a CEO on top and all the various C-levels and below them their departments. It shifts from an org chart like this to something like this, where it's the storage administrator that has to be consulted after a decision is made. Do we want to move ahead with this project? Yes, we do. But first, let's check with Dave. Dave's the storage administrator, and Dave knows whether we have enough storage to be able to move forward with this project. Does that sound like the way things should be? To be honest, Dave is a real person. I've met Dave. Very large telco company I used to work with. Dave was a former database administrator, now the storage administrator. Dave had a massive spreadsheet that basically accounted for all the storage and all the systems inside of IT. And nothing moved forward unless Dave could make that spreadsheet answer the question, do I have enough storage? So for the most part, most of IT is generally unaware of the problem, unaware of Dave. That's Dave the shark right behind the divers there. Companies are unaware of the problem. They basically see IT as a problem at any rate, but they don't see that, there's some denial on the part of the storage administrator, the database administrator, the people who run the infrastructure. They don't see the denial there. They do see that the testers are just kind of biding their time, doing nothing. Same thing with the developers. They're just kind of sitting there waiting for resources to become available. And then, of course, when we are able to provision something, but maybe not everything, everything worked fine in development, it becomes a problem. If we don't adequately QA and test things, it becomes a problem in production. So sorry about all the memes, but I think this stuff is kind of fun. Okay, so let's talk about attempted solutions. Since prod is a big environment and always getting bigger, one of the attempted solutions is subsetting prod so that we can have as many environments as we need, QA test, dev, and UAT, within the infrastructure that we're provisioned. So that means having to take prod and cut away at it. There's an entire software industry around subsetting. It's expensive. It's hard to do. It's hard to take a relational slice of a relationally integrated slice of production that has enough relational integrity. That's what I'm trying to say. It's not easy to do. It's not even easy to say. So that's one possible solution. The thing is that because it's so difficult and time-consuming to do, sure, we can make small environments, but it takes a long time, and we're not meeting our goal of having new environments every 2 weeks to meet the new sprint. So it leads to having to cut costs and time elsewhere. That leads to buggy code. And because these environments take so long to produce, they invariably grow stale and dirty, and they don't do the job properly. They're not good environments for development. They're not good environments for testing. So subsetting is just not a great idea. Then we could try using hardware. In other words, with mirroring, we generally take each volume that's in production and copy all the data to another volume behind it. That's mirroring. We can actually do double mirroring and mirror the volume one extra copy. And then when we need to snap off a copy of production, we can do so using the hardware, snap it off, and turn it into development. And when we need to get a new copy of production, what we have to do is move that volume back into production and resilver it. In other words, resync it with the production mirror set, and then split it off again, and we have our new copy, do our work on it, and then again, go back and resilver it. So where do you think we've saved the time? We can actually create a snapshot very, very easily, but it takes a long time to resilver that volume. We can't refresh quickly. So what we have here with this hardware solution is a very expensive one-trick pony. It can snap off copies very fast, but it sure can't refresh very fast. Okay, so we've solved one problem, but we haven't solved the other problem, and we haven't solved the problem of using full images. Think about it. For production is big. We need not just one volume, but two for redundancy. Then we need a third for dev, a fourth for UAT, a fifth for sit, a sixth for training. That's a lot of storage. That's a lot of snapping, and that's a lot of resilvering. So it's just not as good a solution as we thought it might be. And although the storage administrators love it, we're still back at square one with the storage administrator being on top of the hierarchy. And what's more, they're now deeply embedded into everything that it takes to build an application, because application storage is now provisioned by LUNs and devices. That just doesn't make sense. We have to pre-allocate storage for every copy that we're going to make. And there's a procurement cycle involved with that. It's just very awkward. And now the storage administrator is loving life because they're king. So in a perfect world, we'd like to see a separate, independent environment for each developer and tester. And we're able to snap it quickly to create it, and we're able to refresh it quickly whenever they need new data. But of course, what we've got is the same old, which is a single environment that's being shared by all the developers and possibly all the testers. So here's the problem in a nutshell. It's not easy for developers and testers to share environments because the changes each one makes conflicts with one another. So it becomes necessary to serialize access to the limited number of these environments, which means queuing at the resource. We all know about queuing. So overall project elapsed time takes longer. And because each user destructively changes that shared resource, we now have to have a way to reset or clean up additional development and additional testing that we have to do. Further delays. We just can't have this situation of queuing at the resource. So what's the solution? Let me go back to the early slides of this presentation. With server virtualization, we broke the stranglehold that physical hardware had on application development by creating virtual environments, virtual machines. So we have virtual servers with CPU, RAM, and network and such. We need, for data, the same thing. So the biggest problem when we're cloning an environment from production to non-production is all the duplication of data. Think about it. When you're copying a production system to non-production, or when you're just copying two systems, one from one to the other, when you actually start using that copy, how much of it do you actually use? How much of it do you actually modify? How much of it do you need? If you have a 10 terabyte environment and you're going to make a copy of that so that you can have a dev or test environment, how much is your development or testing activity actually going to be changing out of that 10 terabytes? So what if we had a file system that stored only one copy of each version of a block, of a storage block? And we use copy on write technology, which has been around for almost 2 decades now, to never modify a block, but every time a change is made, to insert a new version instead. And then we let that storage, that file system, if you will, figure out what we're supposed to be seeing, which version of each block we're supposed to be seeing. File systems are actually very good at that. And let the storage maintain these relationships between versions on retrieval. So what we're doing is we're keeping a history of all changes made to a block by storing multiple versions of each block. And we let the storage figure it out, see what we're supposed to see. Now, what if we had this storage and we could make it portable so that any platform, any OS, Unix or Linux or Windows, can use it? How can we do that? We can use network attached storage to make that happen. So we have a storage appliance that has this file system that uses copy on write, and we present the information over network attached storage to any end user environment, Unix or Linux or Windows. So now, instead of cloning the old-fashioned way, by cloning every single byte from prod to dev, say 10 terabytes or 100 terabytes, and copying it across a network, doing so many reads and so many writes, instead of doing that, what if instead we cloned smarter and instead created an appliance in the middle between prod and dev? And that appliance can capture changes incrementally. Whatever size prod is, it can be initialized to that appliance that's in the middle. Prod can be, an initial copy can be made, and it can be compressed. And then as changes are made to prod, they can be captured incrementally. So we're not having to make a full 10 terabyte copy. If prod is 10 terabytes, we don't have to copy over and over and over again 10 terabytes. We copy maybe 10 terabytes in the beginning, and then we're copying just the changes that are made to that 10 terabytes on prod, and we're storing them on the appliance. And then when we want to, because the appliance is storing using copy on write technology, when we want to provision dev, we don't actually move all the data to dev. We project a snapshot, a thin provision snapshot image to dev over network attached storage. In other words, during initial setup of dev, nothing gets copied at all. Because the way network attached storage works is data is not copied over until the application in dev asks for it. In this case, the application could be an Oracle instance. Okay? And then as the Oracle database application on dev makes changes, just those changes, get stored on the network attached storage appliance in the middle, that prod copy. Just the changes are being stored. So in essence, the dev copy is only taking up storage for the number of blocks it changes. So the cost of the clone and the time it takes to produce the clone has gone way down because of this way of doing things. So how does it all work? Overall architecture, again, it starts with, on the left-hand side, it starts with a prod data, a data source, let's put it that way. And usually that's production. In the middle, we have a virtual machine appliance, a software appliance, that mainly consists of this file system that I described. We have change data, I'll say it correctly. We have command and control processes using SSH to connect to the OS and JDBC to connect to the database source itself, again, to issue commands. We then, in an Oracle environment, do incremental backups using Oracle RMAN. In this case, RMAN isn't being used for backups, so to speak, but rather just to do change data capture. We initially take a full backup, pull it over to the appliance and compress it, and then we're pulling any incremental changes that happen after that, and we retain those in the appliance. Now, when we want to provision a virtual copy, we create that thin provision virtual copy in the appliance and then project it to the target database server. What the target database server sees, and the appliance is doing command and control as well, it's using SSH and JDBC to start up an Oracle instance. It then sees an NFS mounted data file. The data files actually reside on the appliance and they're projected over NFS to the target server. So the target database server doesn't need storage because the storage is on an NFS mount back to the appliance. So we can thin provision numerous copies on that appliance and project it using NFS. And that's what we show here. Rule of thumb, if you have a source database that's, say, 10 terabytes, what we need on the appliance, the virtual machine shown here, is, again, about that same footprint, about 10 terabytes. But for that same 10 terabytes, instead of only making one copy, which is what you would get by just simply copying the files from one to the other, this method of cloning can actually produce for you 20 or 30 copies in that same footprint of 10 terabytes. So normally, making 30 copies of a database would take 300 terabytes, right? 30 times 10. But with this method of doing things, by having 10 terabytes dedicated to this appliance and getting 30 virtual databases out of it, 10 terabytes instead of 300 terabytes. And we're not moving the data around. We're acting much faster than that. So we're provisioning these virtual databases in 10 minutes. Pretty good news there. Okay. How does that file system work, this copy on write file system that I mentioned? Well, initially, when we pull a full RMAN backup in, we create an initial snapshot. So all these blocks at the bottom, these gray blocks, they're all the data blocks that were pulled in from the database. Now, of course, there's no database that consists of only 10 blocks. I'm just kind of, not able to draw it any better. So that's all I can work with is 10 data blocks. But imagine there's thousands or millions of these blocks. So we build a file system tree structure with branch blocks above it, finally coming up to the root, which is snapshot number 1. Okay. So whenever we want to see the blocks that belong to snapshot number 1, we navigate downward from the root through the branches to the data blocks. Now the next incremental backup comes in, and it looks like 2 of these blocks, B and C, have been changed. So rather than overwriting B and C and losing that the initial values of B and C, we add, instead of overwriting the blocks, we add a new version of B and C, B prime and C prime. We add it to the file system, and recursively, looking upwards, we copy the branch block which referenced B and C. We make a copy of that branch block, and now it references B prime and C prime. And recursively upwards, we take the root block that contains snapshot 1, and we create a second root block called snapshot 2 that, instead of referencing the original branch block that referenced B and C, it now references this new branch block that references B prime and C prime. So now you can see what I've got are 2 full database backups in the space of 1 backup and some change, right? My original backup was 10 blocks. My incremental was 2 blocks. And yet, from both snapshot 1 and snapshot 2, I'm showing 2 different images of the same full-size database. Okay? So that's how that works. And we can just keep going. Another incremental backup brings in a change to I prime. So we do the same thing. We bring I prime into our image, and the branch block that references I gets cloned, and a new version is created that references I prime instead of I. And going backwards up to the top, instead of having snapshot 2 that referenced this same branch block that referenced I, we now have a snapshot 3 that references the new branch block that references I prime. So that's how we're able to manage so much data in so little space to begin with. Okay? Now, no matter how little space we're taking up, nothing is forever. Eventually, we're going to have to get rid of, the oldest data that's no longer hopefully being used. So when we want to do that, when we want to delete snapshot 1, this snapshot here, does that mean we have to delete all the blocks that came in with snapshot 1? No. Instead, when we want to delete snapshot 1, we look for candidates. Candidates under snapshot 1 are branch blocks that are referenced only by snapshot 1. These other branch blocks are referenced by other snapshot level blocks. So this is the only candidate branch block that's going to go. Underneath it, recursively, we look for the data blocks that are only referenced by this branch block and not by other branch blocks. So the original B and C are candidates for deletion. So when we drop snapshot 1, we don't drop all the blocks that came with it. We just drop these, and so on. Now here's the real fun, and this is where the magic of the thin cloning becomes obvious. Let's say we want to create a virtual database based on snapshot number 2. When we do that, do we have to copy all those data blocks and branch blocks? The answer is no. All we need to do is copy that initial root block, because that initial root block already has pointer references to the necessary branch blocks underneath snapshot 2, which of course have their references to the data blocks. So why is it faster to create a full-size 10 terabyte or 100 terabyte database using this kind of file system? The answer is because it just doesn't take that much work to do so. We copy just the root, not everything else. That's wonderful. And then as changes come in to this virtual database, virtual database snapshot 1 that was copied from the original source snapshot 2, the same thing keeps happening. Let's say block A is going to get modified to A prime prime under the virtual database only. So we bring it into the virtual database structure. We create a new branch block that references A prime prime instead of A. And that branch block is referenced by VDB snapshot number 2, and so on. Everything is done very efficiently. Smarter, not harder. Okay? So I don't know if you've seen The Matrix, but there's a scene in there where Morpheus is being mystical, and the character called Morpheus is being mystical, and he says, at least in this case, he's seen DBAs wasting entire days cloning. I mean, it's got to be the worst job as being a DBA, is cloning environments. Think about it this way. Think of the dental industry, right? You've got dentists. I mean, it's not an exciting industry, at least in my mind. It's not an exciting industry, but the absolute worst of it has got to be the dental hygiene, cleaning teeth. Well, that's pretty much what DBAs must consider cloning, because it's a repetitive job and it's hard to do and it takes attention, but it really doesn't buy that much. It just buys you another database. So their time and their size and their productivity is based on a world that's built on physical storage, and they'll never be as agile as they can be. So then we've got in the next scene, Neo says, "What are you saying? I can copy files faster?" And he says, "No, once you install data virtualization, you won't have to copy files." So that means, whoa, warp drive. What does data and database virtualization mean? Let's talk about some of the use cases. The obvious is accelerating development, testing, and support. We can have more copies. We can produce them faster. We can not only produce them faster, we can refresh them faster. So we've got all these full-size images of databases being produced as we need them and then being destroyed without the loss of anything when we don't need them anymore. So we have unlimited number of full-size copies. We have an interface that allows you to allows testers and developers to manage these databases. Think about that. Taking out the middle person, taking out the DBA for the drudgery of refreshing and rewinding databases. They don't have to do that anymore. The self-service interface can do that on the commands from developers and testers. We can secure the data, and I'll talk more about that. And also, we can prepare for a cloud migration. So first, let's talk about unlimited number. I won't say unlimited. It's not quite true. Do you all remember this episode of Oprah Winfrey where she gave away car keys? Well, we took it and made it seem like the crowd of developers and testers each got their own virtual database. Look how happy they are, huh? Anyway, crazy stuff. It's not exactly unlimited, I'll admit. Like I said, it's roughly for each Delphix appliance, you can really count on anywhere from 20 to 30 copies, maybe more. But it's not unlimited, but it's quite a few. And they're also full size. You don't want smaller sets of data because really removing data from your testing set means you have fewer test scenarios. Removing data means removing reality. Removing reality from the standpoint of test scenarios, removing reality from the standpoint of testing against realistic production. We want full-size systems. You don't want a half a beer. You want a full-size beer. Right now, I want a full-size beer too. Even though for you it's 10 a.m., for me, it's almost 7 p.m. because I'm in Colorado. Self-service. The issue here is that you want to be able to allow people to do what they're capable of doing. And if you can provide an interface that simplifies the task of refreshing a database from its source, bring in a new copy from its source, or rewinding a database back to a prior point in time without complex CLI commands or anything like that, then that's better. And here, according to this flowchart, if a tester wants, in the current situation, if a tester wants to have an action like this performed on the database they're working with, they have to talk to their manager, who has to talk to the database administrator, who then has to talk to the system admin, who then has to get more storage from the storage admin. And then everything, once the storage has been allocated, it goes back to the system admin to set everything up. Then the DBA has to set up the new database. And finally, days later, or even weeks later, the tester gets their new database, the way they want it, rewound or refreshed or whatever. But with data virtualization, when you have a system that's built to do this, I kid you not, the tester can press the button and 10 minutes later have the database rewound to and the application rewound to wherever they need it. That's what this capability is. So it's essentially like, in many ways, it's essentially like operating a jukebox. You don't have to be a DJ to operate a jukebox. You just have to be able to drop a coin in. And the same thing is true here. You don't have to be a skilled DJ. You don't have to be a skilled DBA. All you have to do is press the appropriate button, and you'll get exactly what you're asking for. Now, very blithely, I've been talking about copying data from production to non-production. But the savvy among you probably already know that that's not going to be available to us for much longer. Production data has confidential data. We have to do something about that because we can't let developers and testers necessarily see that data, the confidential data. That's how data breaches occur. It's not that developers or testers themselves are untrustworthy, but they're just simply not authorized to see it. And the other thing, too, is that there are so many copies that we're making of production for dev, for test, for this sprint, that sprint, the other sprint. If you have 30 copies of production out there, you're bound to lose one, right? So in that situation, one additional capacity of making these virtual copies has to be to secure the data. How do you secure cloned data? It's not just encryption, because encryption is technology that allows authorized users to view the data. Well, the thing is that developers and testers are authorized, so that doesn't do the job. What we do have to do is mask the data. We have to obfuscate the data when it moves from production to non-production, so that the data that developers and testers are working with is obfuscated. It's no longer confidential. It's been permanently changed, and it can't be changed back. But obfuscation is not just simply random scrambling. Stop and think about it. You can break applications just by scrambling data. Think about credit card numbers. Think about national IDs. Those have algorithms built into them. Credit card numbers, the first digit means something. The first 6 or 7 digits represent a bank or financial institution. The middle 8 or 9 digits are an account number. The last digit is a checksum of the first 15 digits. You scramble that, you're going to break your applications. There's other situations like that. You can't just scramble geographic locations. It doesn't make sense to convert Sydney, Australia, New South Wales into, I don't know, something scrambled like San Francisco, London, England. It just doesn't make sense. You can't just scramble that data. You have to change it in a meaningful way. So data masking is a big part of allowing data to get to developers and testers. And that's built in with data virtualization as well. It's a huge, huge area of functionality, but it's something that's coming on very, very soon. Many of you have heard about GDPR, the new regulations coming from the European Union. Anybody who does business with the European Union is going to have to prove that they can protect data. And obfuscation and masking is a big part of that. Obfuscation, masking, and non-production, doing software development. Okay? And that's all happening starting May next year. So we have to be ready for that. And how long is it before other countries adopt these kinds of regulations? The European Union is kind of a test bed for it. But you realize it's got to happen. We've got to have these kind of protections, because what we've been living through in terms of data breaches now, it's not going to work. The liability is too great. Something else that happens with virtual data. Okay, I know this is going to start some kind of argument, but I'm going to say it anyway. Legacy Unix is dead. Okay? Solaris, AIX, HPUX, dead as a doornail. Oh yeah, it's still working pretty good. But the fact is that moving forward into co-location centers or public cloud environments, everything is Intel. The only thing that really works in public cloud or runs in public cloud is Linux on x86 and Windows on x86. Only the vendors are going to be moving Solaris into public cloud. AIX is only going to be moved there by IBM. HP isn't even going to try with HPUX. I personally don't know why anybody is still using HPUX except they're trying to get off of it. So proprietary Unix is dead. In order to get to the cloud, you first have to get to Linux if you're on Oracle. And migrating from Unix to Linux is, even though it's been available in Oracle for over 10 years now, it first came out with Oracle 10G, and that's the Oracle RMAN convert data file command and convert database command. It's been out there for 11 years. And how many of you, stop and think, how many of you have actually used this capability? The reason is that it's a long, drawn out, and it's a very expensive procedure. It involves temporarily making 3 copies of your source database. Well, having 3 copies of your source database. You have your source on UNIX. You have to make a second copy of that source on UNIX and put it immediately into read-only mode, because the migration utility, the migration procedure, according to RMAN, is going to use transportable table space to convert the data files from Unix to Linux. So that's 1 copy of your source database that's running, a second copy that is copied from the first and is put in read-only mode, and then a third copy that's converted to Linux. Now, that second copy can be deleted, of course, but for a period of time, you need 3, the room enough for 3 environments. Data virtualization and thin provision VDBs make this faster and simpler, and it's built in. So if you're planning on a cloud strategy and you're currently on legacy Unix, you got a lot of work ahead of you. Data virtualization helps with that. Finally, testing. Testing with data virtualization is marvelous. If you can just create as many copies as you need, and if you can rewind each of your environment copies in their entirety back to the same point in time so that you can redo destructive testing over and over and over again, life is good. If you've, here's the age-old joke, I guess. If it takes one woman 9 months to produce a baby, why doesn't it take 9 women 1 month to do so? Ha 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 ha. Well, that's not very, realistic in real life, the way you put it that way. But it is possible to take a large task and make multiple copies of something and distribute it amongst several people. If you've got a large amount of test scenarios that have to be processed, then you can, in fact, instead of having one tester take 7 weeks to do something, you can have 7 testers with 7 environments take 1 week to test through something. And likewise, when testers test something, they have to rewind. They have to do their destructive test, and if it fails or if it succeeds, they have to rewind to the beginning again, reset everything, and then do the test again, maybe with different variables. Rewinding is very, very endemic to the task of testing. And with data virtualization, rewinding is a matter of minutes, no matter how large your application or database environment is. And when you can make copies, as many copies as you like, in just a few minutes, then A/B testing becomes a fairly easy thing to do. If you want to test, with scenario A, and then you want to test in a similar environment against scenario B, and then compare the 2 scenarios, well, you can do that a lot easier. Again, when making copies takes no time and no storage, it becomes very easy to do that. Here's a great example of real life workflow between testing and development. Let's say we've got a QA tester, we'll call her Jane, and a developer, and they're having this conversation. The tester says, hey, I found a data problem in version 3.2.2a of the application we're working in. And the developer says, can you bookmark that and share it? Bookmark it, share it. Jane, the tester, says, yeah, I created a bookmark against my application and database, and I've shared it with you. Here's what to look for, and it's in the comments on the bookmark. And now the developer can say, hey, look, I took your bookmark, I restored a copy of the database from your bookmark, my own copy of it, and I see the problem. So the great thing about this conversation is it doesn't have to happen in real time. It can happen over email. Jane doesn't block Mary or stop Mary from doing what she's doing. The fact that she's not available doesn't stop Jane from progressing. That's the great thing about this. So we can create bookmarks at different points in times on our database, and other people can make copies of that database at that point in time and restore their own copy for their own independent use. That's amazing stuff. So I think I've got about 5 minutes left, and I'd just like to finish up by saying access to data is the constraint in IT today. Having only 3 or 4 non-production environments is wrong. We've always lived with it. For the past 30 years, we've lived with it. But the fact is, having only 3 or 4 copies of production in non-production for software development is not the way to do things. If you could, you'd want to have each individual having 1 or more of their own private copies of everything. What is stopping you from doing that? Data virtualization is the solution. Let's reverse the 80-20 rule for testing. Instead of waiting 80% of the time and working 20% of the time, let's reverse that so that we're waiting only 20% of the time and working more. Get better testing results, get better development. And always remember that virtualization is the process of converting hardware into scriptable software. So when we virtualize, we also make things available for automation. And automation equals getting things done faster. So that's what I had today. Let's see if we have any questions. I'm not sure how to ask.
Hi, team. I have asked, but looks like no one have any questions.
Okay. Very
up
good.
to this point.
Okay.
And just asking one more time, anyone have any questions? I have asked by the chat. Now, looks like there's no questions up to this time. If anyone have any questions, please, you can contact him by his contact information that he shared in the presentation. And you also can send the questions to me and I can forward to Tim too.
Thank you very much.
Thank you, Tim. Have a wonderful evening.
Thank you. Have a wonderful day.
Bye-bye.
Bye-bye.